Hello, everyone. All right, so offshore wind energy will be a significant source of future renewable energy generation. Wind energy is already 10% of the total electricity generation capacity in the US, and it accounted for 22% of newly added capacity in 2022. Even if going forward, the priorities shift in terms of the energy mix, it will continue to be a part of the mix, especially for countries which do not have fossil fuel reserves and so on. And I should clarify what I mean by offshore wind energy is when we place these huge wind turbines out into the ocean or into the Great Lakes, etc. As you can see from the image on the right, it should be very apparent that this problem would be very challenging engineering-wise, both in terms of the design and operations of the turbines. And computer simulations have a very important role to play in this, be it assessing the availability of the wind resource, modeling the interactions between these huge waves and the turbines, or predicting and preparing for extreme events, which are even more extreme out in the ocean, right? And not only are we interested in how these turbines respond to the atmosphere around them in terms of, okay, how much power are they going to generate? What is going to be the blade loading, etc. We are also interested how these huge wind farms are going to affect the local ecosystem, or maybe wind farms that are 10 kilometers away, right? So we are interested in all these problems, and computer simulations play an important role. So if we want to do effective wind farm simulations, we need the atmospheric data around it as initial and boundary conditions. So there is the mesoscale atmosphere flow and the microscale wind turbine environment. And the process of filtering down the flow from the mesoscale to the microscale is known as downscaling. And the physics that are important for the turbine, like turbulence in the flow, kinetic energy contained in the flow, etc., need to be captured correctly during this downscaling process. And similarly, during the upscaling process, right, when feeding back the data from the microscale to the mesoscale. Now, traditionally, the mesoscale and microscale models are developed independently just because the length scales are so different, and so the physics that govern these scales are so different. And the traditional way to couple these two kind of solvers is a file-based coupling, which basically means we would run a mesoscale simulation, write out the solution in time files, and then we would run a microscale simulation. We would read in those files and use the data as initial or boundary conditions. Of course, the file system would be a big bottleneck here in terms of the kind of performance you could get. So instead, if you could do an in-memory data transfer between the mesoscale and the microscale, then that would be, of course, more efficient. It would allow you also to do a two-way coupling where you can also feed back the data from the microscale to the mesoscale, apart from driving the microscale solver using the mesoscale data. Now, there do exist nested models that can nest a microscale solver domain within a mesoscale solver domain, but these cannot run on GPUs and do not have the capability of dynamic mesh refinement. So what do we need? In summary, for computationally tractable and accurate simulations of such wind farms, holistically, we need numerical solvers that are designed for the respective length scales, mesoscale, microscale, and the physics. So for example, at the mesoscale, we usually talk about compressible flow solvers where you allow the density to vary. For the microscale, we talk about incompressible flow where you don't allow the density to vary, and so on. For each of those solvers, we need the supplementary modeling capabilities which are relevant for real-life problems. For example, for those big mesoscale solvers, they should be able to model the different type of land terrains, right? For the microscale models, they should have ability to model a wind turbine using actuator models or a wind farm using parameterized models and so on. And finally, for performance, we need the adaptive mesh refinement and the capability to run on GPUs. That brings me to this project, which I have been contributing to, which involves the in-memory coupling of two such solvers, which is the Energy Research and Forecasting Code, ERF, that solves the compressible flow atmospheric model equations, and the AMR Wind Incompressible Flow Solver for the flow in the vicinity of a turbine. Both of these solvers are based on the AMRX framework that enables this capability to run on GPUs or to do adaptive mesh refinement, right? And the goal, of course, is that during this in-memory simulation, the ERF solver will drive the AMR-Win solver with the high-fidelity atmospheric conditions, and the AMR-Win solver will return the high-resolution information back to ERF, and they will run in lockstep with each other without the need to transfer data through files, for example. And of course, this work has been in collaboration with several other developers and contributors at Berkeley Lab and at the National Renewable Energy Laboratory. In terms of the mechanics of the data transfer, this uses the multi-block capability within AMRX that allows you to map one data structure to the other and actually instrument trigger the copy of the data between the two solvers. And here's what the algorithm looks like, right? So we first advance the mesoscale solver, which is ERF, from time t to t plus delta t. Then we populate the AMR wind boundary with the new time solution because AMR wind is an implicit solver. Then we advance the AMR wind solver from to the new time. And then if we are doing the two-way coupling, we populate the region of overlap within the ERF solver with the high resolution information from AMR wind. Now, when we advance the ERF solver, which is the mesoscale solver and the compressible flow solver, we need to allow it to do multiple time steps for each step that the microscale solver takes. This is because the compressible flow solver has more stringent time step restriction. For example, for a Mach number of 0.1, it would have to have a time step which is 1/10 of the microscale solver. So it needs to take, for example, we should allow it to take 10 time steps, right? And so this capability has been implemented. Apart from the temporal resolution, we also need to allow both the solvers to have different spatial resolution at the interface so that we can run both solvers at the length scales for which they were designed, right? And so this capability has also been implemented. Finally, coming to AMR wind, we have implemented a boundary condition in AMR wind which, after receiving the data from the ERF solver, is able to, because remember, AMR wind is an incompressible flow solver, whereas ERF is a compressible flow solver. So after receiving the data from ERF, it scales the outflow to match with the inflow, and so it makes sure that the velocity field is solvable in terms of it being divergence-free. It also allows you to handle flow going both in and out of the AMR wind domain via this boundary condition. So I have an animation, which I'm guessing would be probably too slow, but essentially what this would show is that this is a Couette flow with a linear velocity profile, where the bottom plate is stagnant and the top plate is at a finite velocity, and you have a scalar bubble that kind of convex along with the flow, which would go from left to right. And the red box shows where the AMR wind domain lies within the ERF domain. So with this kind of a simple flow, we are able to demonstrate the ability of the one-way coupling for the flow, for the data to be transferred from the mesoscale to the microscale. In summary, we have the driver in place that exchanges the data between the two solvers using the multi-block feature. We have implemented the new boundary condition that allows the AMR wind solvers to accept the data from ERF and make it numerically solvable. We are working towards simulating a one-way coupled atmospheric boundary layer with a surface model, a surface roughness model, velocity perturbations, turbulence, etc. And I hope to present that at the SIAM conference next month, the CSC conference. So if you're there, come check out our session. We also have the basic infrastructure in place for a two-way coupling, which would be developed and tested in the future as part of this project. And apart from this, there are many other challenges this kind of a coupling opens up. Just as an example, turbulence modeling, right? If we run both of these models at a different length scale, the mesoscale model uses something called planetary boundary layers, or Reynolds Everett Navier-Stokes, for the turbulence model, whereas the microscale model uses large eddy simulations. So the question is, how do we transfer the turbulence from one type of a model to the other? So this kind of a coupling opens up a lot of such problems going forward, including performance-related issues such as load balancing and so on. So if you're interested, check out the GitHub repository. And this work would enable more holistic and effective wind farm simulations in the future by using such a coupling capability.